Alright, hello everyone. I know it's been a while, but it's good to be back recording these math videos. So today we're going to be looking at regular surfaces and tangent planes. So we begin with a couple of definitions. So let's say we have a subset of Rn. Some set V is open if V is the intersection of S and an open set in Rn. We'll later learn in topology that we say that S inherits a subspace topology for which this is true. But for now, we're just going to say V is open under those conditions. So a neighborhood of a point P in S is a subset of S that is open in S and contains P and contains P. So let's say we have a subset S. And let's say we have an open set, and this is open. The intersection between these two sets is going to be open in S. And furthermore, if we have a point P in that set that's open in S, we say that this is also a neighborhood of P. So now we continue with the definition of a regular surface. So a set in R3 is called a regular surface if each of its points has a neighborhood in S that is diffeomorphic to an open set in R2. So let's say we call the neighborhood V, and we say that there's an open set, U, which is a subset of R2, open set in R2, and there's a diffeomorphism from U to V, which we will call sigma. This diffeomorphism is called a surface patch, or it is called a coordinate chart. And furthermore, a collection of surface patches that cover all of S is called an atlas for S. So let's take a look at what that essentially means. This is our regular surface, S, if given any point, we can create a set that's actually let's not make it 3D. If you can see, you know what? It might make it more confusing if I made it look sort of 3D like that. So you know what I'm going to do instead? I'm going to do that. So it looks, maybe add like some peaks and troughs. But the point is, if we have a point P, and we can give it a neighborhood that's open in S, which we'll call V, we have our O2 here, and we have an open set U, and there must be a diffeomorphism, which is differentiable and has an inverse that is also differentiable. Furthermore, let's say we have a regular surface like this. Maybe we have an open set like this, and then we have an open set like this, and then an open set like this. Actually, I shouldn't do it all in one color. And then maybe an open set like that, and finally an open set like that. So all of this is in there, all of this is in here. This is a very bad drawing, but I'm trying to convey it. This is an example of an atlas. So let's move on to a proposition. If S is a regular surface and sigma from U in R2 to V in S is a surface patch, then for all Q in U, the linear transformation, which we call d sigma Q, from R2 to R3 has rank 2. So let's prove this. Suppose that P is equal to sigma of Q. So Q is right there, and P is right there. The chain rule says that the derivative of the function sigma to the negative 1 composed with sigma at the point Q is equal to the derivative of the outside function at sigma of q, which is p, composed with the derivative of the inside function at point q. But we know that this function is the identity function because sigma is a diffeomorphism, which necessarily means it is invertible. And by the way, we're extending all of these functions to R2 and R3. And the identity has rank 2. I could go deeper into this, but that's sort of more linear algebra, so if you don't already know linear algebra, just take my word for it. And therefore, it must mean that the rank of a composition of two linear transformations must be less than or equal to the rank of the first. So, d sigma q must have rank 2. So now let's talk about regular values. So let's say we have an open set in R3, and we have a function on that open set to R, and we have that f is smooth, so differentiable, and we have some real number lambda in the image of f. So the set, which we denote as f to the negative 1 of lambda, which is the set of all p in U, which is the domain, such that f of p equals lambda, that specific lambda, is called the pre-image of lambda. And furthermore, we have that lambda is a regular value of f if for all p in the pre-image of lambda, the Jacobian matrix for f at p is not the zero matrix. So in other words, the partial derivative of f with respect to x at p, with respect to y at p, and with respect to z, they cannot all be 0. So there's a theorem that's associated with regular values, and this is actually how the other book that I've read on intro differential geometry, which is written by Do Carmo, introduced regular surfaces. So CAP introduces regular surfaces a slightly different way from what I recall. I might be wrong though, so if I am, I'll correct myself in the comments. But basically, the theorem states that if lambda is a regular value of f, then the preimage is a regular surface. So that's a bit about regular value. Oh, that's a bit about regular values. So let's move on to parametrized surfaces. So that is essentially a smooth function, which we'll call sigma, from u to R3, where u is in R2, such that for all q in u, the derivative of sigma at q has rank 2. So we need to be very specific here. A regular surface is the set, whereas a parametrized surface is the function. In the same way the parametrized curve is the function from R to R3, or an interval on R to R3. And every surface patch for a regular surface is a parametrized surface. So if you're wondering about the similarities between the two, there you go. But you can't really use them interchangeably. So let's continue with a proposition. Oh, proposition. So if we have sigma from u to R3 is a parametrized surface, then for each q naught in u, there is an open set, there exists an open set, which is a subset of u, containing q naught, such that the image of the open set u tilde is a regular surface. Regular surface covered by a single surface patch. So hopefully this should sort of make a little bit of sense. Basically, what we're saying is that if we have let's say we have set u, and then we have sigma u, and then there's a function sigma. And note that this is the parametrized surface. If we choose any point on u, let's choose this one, q naught, then we can find some open set. I'll make this an open set, and we call this u tilde, which is a subset of u, and it's containing q naught such that what we defined as S is a regular surface. So what we are saying under these conditions is that we can choose any point so that there's an open set surrounding it, such that if you apply sigma to it, then the result is a regular surface. I'm not going to go through the proof of this because I feel like I've already spent a long time on regular surfaces, but it's a good thing to think about geometrically. So now we've discussed regular surfaces in great detail. So let's do a bit of discussion on the tangent plane. So let's say S is a regular surface. A regular curve in S is a regular curve in R3 where the trace is in S. So if we have a regular surface S like that, then a regular curve might be something like this. The important thing is that every single point on the trace of the curve must be within the surface. Now the tangent plane to S at some point is the set gamma prime of 0, where gamma is a regular curve in S, where gamma 0 equals P. So what are we saying with that? Let's say we have a regular surface like that, and we're looking at a point P. There's a curve going this way, so there's a velocity vector that way. And of course it can be at different speeds, so it could be like that as well. It could be twice as long or thrice as long. There's a curve going this way, so there's a velocity vector this way, this way, this way. And as you can see, these vectors start to form a plane of sorts. And that's how we get our tangent plane. So let's say that U and V are the coordinate variables of U, where we have a coordinate chart sigma. Then the tangent plane at point P is equal to the span of the partial derivative of sigma U, or the partial derivative of sigma at U with respect to U at Q, and the same thing for V. And furthermore, this implies that because there are two vectors spanning the tangent plane, that means that, and these are two linearly independent vectors spanning the tangent plane, so it is a two-dimensional subspace of R3. Now, just a few more items before I end the video. Let's talk about the derivative. So, the derivative of a function f at the point P in S, where f is a function from S to Rn, it's the linear transformation dfp from the tangent plane at point P to Rn, defined such that if we have some for all v in the tangent plane of P at P, the derivative is equal to the derivative of the composition of f and gamma at 0, where gamma is any regular curve in S, where gamma 0 equals P, and gamma prime 0 equals V. So what that means is, you know what, let me zoom back in. The question you might be asking is, what is this f composed with gamma? So let's go through this. Gamma is a regular curve, so we're going from R to R3, and this regular curve is in the surface. And we're given that gamma of 0 is P, and gamma prime of 0 is V. And f of whatever, if we take the function f of, let's say we take the point P, it just maps to some, I need to emphasize this is Rn. The trace ends up being some curve. So the derivative is simply the this is gamma, this is f composed with gamma, is simply the derivative of this function at 0. So hopefully that was sort of somewhat easy to follow. Maybe that sort of cleared things up. Hopefully it didn't make it more confusing, but let's continue with proposition. If we have a function between two regular surfaces and it is smooth, then its derivative at any point for all p in S1, at any point p in S1, simply takes the tangent plane of S1 at p to the tangent plane of f of p at S2. And now we can discuss the inverse function theorem. Again, I sort of didn't do it justice last time, but now I have space on my computer, more space on my computer, so hopefully I should be able to discuss some more. But this time we're going to be looking at it for surfaces. So, suppose we have two regular surfaces, S1 and S2, and we have a smooth function, f, which goes from S1 to S2. So, if we have a point P in S1, sorry for the messy handwriting, but if the derivative from TPS1 to TF of PS2 is invertible, then F restricted to sufficiently small neighborhood of P, S1, is diffeomorphism onto its image. And this image is a neighborhood, which is a neighborhood of f of p in S2. So the proof is pretty long, so I'm just going to state the geometric meaning of it. So let's say we have a regular surface that looks sort of like this. Maybe it's kind of wacky. And it is diffeomorphic to this regular surface. So let's say we have P and we have f of P. So if, you know what, forget what I said. It's sort of late in the night, so. So this is not diffeomorphism, this is F. So if DFP is invertible, so that's basically, you know what, let me make this the tangent plane at P, and then we have the tangent plane F of P. Then we can create a neighborhood such that this is a diffeomorphism. So it's invertible and differentiable. So that's essentially what the inverse function theorem is saying. If we have invertible derivative at a point, then we can create a neighborhood surrounding the point such that its image with regard to f, the two are diffeomorphic. So that's basically it for today. Thank you for listening, and I will see you in the next video.